As many can attest, when you join the Globebusters community, you are given a new set of eyes. Now, we've studied Earth science before, but now that we've been given a new set of eyes, it is time to go back and tell you what we see. This is Modern Earth Science Destroyed. Okay, welcome everyone to Globebusters. Good to be back. And today we've got a nice short presentation. We're doing a textbook reading on map projections. Before we get into that, let's introduce the panel, and we'll start with you, Karen. How's it going?
It's going great. Happy to be here.
Okay. You made an appearance on Mark Sargent's channel on Strange World recently. How did that go?
It was good. It was good.
Yep.
It was good to hang out with Mark and DJ and stuff. A little late for me now, but it was fun.
Yeah. We love the energy you bring to that show. It was really fun seeing you there again. Make you kind of miss it?
A little bit, yeah, but also I like going to bed early and getting up early.
Yeah.
I like having a regular schedule.
Yeah, my wife's been doing the same thing ever since her Sweden trip. She's been like waking up like really early in the morning, and she's like, actually, I enjoy this. I enjoy going to bed early and waking up early. So I'm like,
yeah,
I'm not gonna fight it. It's a really good thing to be on like right before school starts back up again.
it's like easy. It's like more with the circadian rhythm of what you're supposed to be with,
Absolutely,
going with the sunlight. So I enjoy it.
It's a weird thing for me because I work graves, and so I'm constantly fighting what my body just naturally wants to do.
Oh yeah, that's right. Yeah.
Yeah. How about with you, Cami? How's it going?
Oh, it's going really, really good here. Just doing my thing.
Just doing your thing. Okay.
It's good that it'll be the short show on that, because that was a short intro on it. So the little short show will go really cute with the short intro.
Yeah. It's gonna be a nice short one today. I've only got there's a whole bunch of pages here, but don't let them get you all kind of.
I don't know if you can all hear me, but busy? I don't hear you.
Oh, sorry. A little bit better. Can you hear me better?
I can hear you now.
Okay, so there's a whole bunch of pages here, but don't let that throw you off, because we're only going to actually be reading from 3 pages here. Okay, 3 pages here. That's it. But they're really significant pages that I think everyone will be able to take away, and these are ones that people are going to want in their archives because they are so effective against trolls. Okay. So, unless there's something else you want to talk about that you've got going on recently, we can get started.
No, go ahead.
Okay. So I'll get started here with, this is the high school textbook, and as before, we also have the college textbook that goes side by side, and it's interesting how much one kind of repeats the other, even on the most basic of stuff. And so we've got like different kinds of map projections, and what really kind of catches my attention is the reading of the map, and about how they've got symbols and scales, and it kind of talks about like the words to remember, like legends. Okay, a legend, a scale, and like those are stuff that people are taught in elementary school. So I'm like, why are they teaching that and emphasizing that in college? It's kind of a weird thing to me, but yeah, that's college level for you. So there's I like the wording in the high school textbook a little bit more. It flows off the tongue better. I think that was the advantage of this. Okay. So a globe is familiar. A globe is a familiar model of Earth because a globe is spherical like Earth. A globe can accurately represent the locations, relative areas, and relative shapes of Earth's surface features. A globe is especially useful for studying large surface features, such as continents and oceans. But most globes are too small to show details of Earth's surface, such as streams and highways. For that reason, a great variety of maps have been developed for studying and displaying detailed information about Earth. Does anything stand out to you about that paragraph?
Most globes are too small to show details about Earth.
Okay.
That's a true statement.
Yeah.
It says a globe can accurately represent the locations, relative areas, and relative shapes. And yet, if you look at all of the different globes, they all seem to have all different proportions on it. In fact, I was noticing that the new animation did a lot of, just like if you remember pictures that they took of the blue marble, and all of them had different continent sizes and different complete aspect ratios and that of it. If you start looking at globes, you'll see that if it accurately does this, why aren't these globes looking the same? Why is it so squished here, so spread out here? And it just lines on a grid, and why are there differences on it? The thing when they say that you can do it, I haven't yet to find a globe, and I've looked, but the sticker on all of them says it's for display only, not for educational or scientific purposes. So
yeah, I've seen that so many times. Just the actual sticker on the bottom of the globes. Yeah, not for educational purposes. And so I think that's a great point here, because the way it's worded, it really does sound like it's saying that, oh, the globes are useful, but they're also not useful at the same time. Right? That's the whole thing right here. Most globes are Most globes are too small to show details on Earth's surface. And so this is kind of downgrading the whole globe thing. And that's downgrading the whole globe thing. And I also noticed that this whole first sentence here, or two sentences, they're both trying to go to war with the flat Earth, which is really interesting. It's like, oh, because the globe is spherical, and they got to continually re-emphasize that all throughout the book, even though they're not really doing anything to put more on the table for that. So this is a little part from the college textbook, and I thought this was funny. Okay. No flat map can maintain a constant distance scale over Earth's entire surface. The scale on a map that depicts a large area cannot be applied equally everywhere on a map. On maps of small areas, however, distance distortions will be minor, and the accuracy will usually be sufficient for most purposes. Okay, so this is like another big thing that's really attacking the flat Earth. But then all of a sudden it starts to get into some other things, but we'll save that for later.
Well, can I just interject right here?
Absolutely, go for it.
If you look at how maps are made, no flat map can maintain a constant distance scale over Earth's entire surface. But if you look at how maps are made, maps are made with their relationship to objects in the sky. So that's not an
like
exact
Polaris
science.
and the sun.
Right,
Yeah.
exactly. So they're basically straw manning the discrepancies that happen when you relate the sky to the Earth and make your map that way. It's not perfect, right? Like there's still minor adjustments. You have to get down to a smaller scale and a smaller map before you get really accurate. So they're basically just saying, oh, it's because, I don't know. It just seemed like a little bit like they're just sort of throwing it in there to keep I don't know. Does that make sense?
Yeah. I think so. Yeah. I think
it can't be like they're basically telling you, oh, a large scale map, like the globe is gonna be inaccurate. Of course it is, and you know, but they're giving you a BS reason why.
Yeah, yeah. They're fighting the flat Earth, and they're just not doing much to actually support their claim on that. It would be interesting if they would actually like provide examples, but they never do. That's just kind of troll speak. You know what I mean? Oh, the flat earth is wrong, but we're not going to show you how and where and why it's wrong, you know? Yeah, it's just kind of reification fallacy. That's what Austin would say. So the reification fallacy. So I like this first paragraph. It's kind of a big deal. How scientists make maps. The science of making maps is called cartography. Cartography is a subfield of earth science and geography. Scientists who make maps are called cartographers. And this, I'm thinking about portrait painting. That's kind of what you were talking about, Karen, is you're taking something and you're painting a picture of it. And that's what cartography is. This is where science and art end up overlapping right here, because that's what you're doing is you're making a drawing. That's what a map is. It's a drawing of land, right? Unless you're using like a photograph or something like that from a plane, and then that you have kind of an aerial view that way. Sorry about that. Any thoughts on that art and map making?
Not so far.
No. I just think it's basically telling you that the globe is a generalization. It's not super accurate. It's a
Yes.
generalization.
Yeah. And kind of that acknowledgement ends up making a big deal. Now go ahead and read paragraph, or this third paragraph. Cartographers use data from a variety of sources to create maps. They may collect data by conducting a field survey. Shown in figure 1, during a
Kyle,
field
you've
survey.
gone again for me. Is
What's
Kyle
up?
gone for everybody else in the chat, or is it just me? Am I special?
I'm sorry, I can try to adjust that real quick for you.
Oh, there you go. You sound good now.
Okay, weird. Okay,
I still don't hear Kyle.
You don't
you can't hear
Kyle?
me.
No, are you hearing him?
Mm-hmm.
Okay,
I hear
I'm trying
you
really
loud
hard
and
here.
clear. That's crazy. Okay,
Is
I'll
my
just
mic
think it's me
too?
that's dropping
I'm
out.
trying to get closer to my mic here, but maybe that's the problem. I'm not sure if it's a problem or helping it or not helping it. Okay, so
the chat's not saying a thing.
okay,
So go ahead.
let
It's
us
just
know in
me
the
that
chat, please.
doesn't have it. It's very strange.
Okay, so during a field survey, cartographers walk or drive through an area to be mapped and make measurements of that area. The information they collect is then plotted on a map. Because surveyors cannot take measurements at every site in an area, they often use their measurements to make estimated measurements for sites between surveyed points. So this is right what you're saying, Karen, is there's a lot of guesswork that gets put into map making. And so you can't just point at a map and say, this is law. You know what I'm saying?
Yes. The more
And-
localized you get, the more detailed the map will get, and things will change. Even it might be even just a little bit, but it does. It's sort of
Yeah.
like the whole measuring the coastline, like that whole thing where it's like you could say, oh, they have so many miles of coastline, but if you actually measured every little nook and cranny and curve of coastline, you're going to end up with like 8 million miles of coastline.
The coastline paradox. That's the term
Yeah,
for it.
yeah,
It's,
the
it's
coastline
literally
paradox.
called the coastline
Exactly.
paradox.
The smaller you get, the more detailed things get, so the globe is very much just a generalization.
Yeah, you sail around an island and every time you're going to get slightly different measurements. So yeah, absolutely. And so I really like this concept of kind of just acknowledging the margin of error. And this is like a unique thing to actually see it in the textbook, because that's something that I've seen way too many trolls do, is they just refuse to acknowledge that margin of error. And the big question that kind of is a big deal for all of us is really kind of identifying just how big is that margin of error. You know what I mean?
I guess
Can you
it
still hear me?
depends on how much. Yeah, I guess it depends on
Okay.
how much you zoom in, huh?
Yeah. How much you zoom in? Okay. By using remote sensing, cartographers can collect information about a site without being at that site. In remote sensing, equipment on satellites or airplanes obtains images of Earth's surface. Maps are often made by combining information from images gathered remotely with information from field surveys. I think you're just talking about that a little bit, but so he's supposed to be doing some kind of remote sensing. I'm not exactly sure how he's doing that there, but this whole thing gets me thinking about uh, looking at the Google Earth images and Google Maps and how you can see what it looks like folds in a map or something like that. Okay. You can see these strips kind of going vertically. And then it gets really apparent when you start looking at water. You can see these strips. And so what happens is you get an aircraft going up above and it's taking all these images, and you can see the rows or columns that it's actually moving along. And then they're taking all of that and stitching it together. And this is all a really big deal. And then I always find it really funny how they end up covering up the oceans. That's a literal cover up, right? Yeah.
Yeah.
So this would be kind of remote sensing stuff. They claim it's satellites. I don't care what you call it, but I don't. Yeah, if it's a satellite that's taking the image, it's definitely not something like that. You know what I mean? A satellite.
No, they could be. They're just using high altitude planes for that.
Yeah, we've got this kind of stuff going on, right?
Yeah.
So this would be a drone that's doing the remote sensing. I suppose something like this could also be over there taking pictures. They've got spy satellites out there on balloons. Yeah. But the big question that I always like to ask is, okay, why would we need these if we've got those? If we can see billions of miles out into space using our super Hubble
Your
telescope,
tax dollars at work.
yeah, or tax
We've
dollars at
already
work,
got those, so yeah,
just turn it around at Earth, and
we
we
need
would
it all.
never ever need
We
this stuff.
need it all.
Yeah, we would never ever need this stuff for pictures. If yeah, and we wouldn't need these. We'd have much larger strips when it comes to all
Mhm.
that. Yeah.
Right.
So that's a really big deal. And so this kind of margin of error, the little things that stand out to you, it makes a big difference. One of the things in another chapter that I noticed here was, is there anywhere that isn't mapped? And I thought that was a significant thing in this textbook. And it's talking about how we've got caves that are still being mapped today. They haven't completely mapped out Mammoth Cave in Kentucky. And they're also talking about
There's
a lot of
caves
things
that they
under the
don't even
jungle.
know exist.
Yes, absolutely. Yeah. Yet they're still claiming to know everything about the interior of the earth, right?
I think all of Appalachia is riddled with caves that go into the mountains for who knows how far and how deep. Like
Yeah.
it's insane. There's no way they could ever know all of it. And that's just
Yeah.
one area that I know of.
The bottoms of lakes are still a big mystery. The bottom of the ocean is still a big mystery. They've got they're
The
still
bottom of
uncovering new pyramids.
is that no, that's something else. But Montezuma's Well in Arizona.
Yes, that's not too far from me. So,
They don't even know. Have you been there? They don't even know
No.
where the water comes from for that lake. And they have like the old cave dwellings in the side and stuff, but they talk about how like they've dove in there and like looked at it, but they don't know where the water comes up from the bottom, and they have no idea where it comes from.
Yeah, it's kind of really weird
Comes
stuff.
from
So,
Sheol.
a lot of so then there's the underneath all of the jungles. I was just reading the other day about them discovering new ruins recently discovered through these planes and drones that they'd fly over the jungle and try to use this remote sensing to figure that out. So a
Like
lot of the world
LiDAR?
is LiDAR is one of them. I think that was one of them. I don't remember exactly what it was called, but exactly how much is not discovered yet, because so often we think about the Truman Show and, oh, the world's already all been discovered already. You know what I mean? How often we get that approach, but this is an instance of the textbook saying not quite. There's still quite a bit to be discovered still, which is a different perspective, because we get so lost in, oh, it's already been discovered already. That's kind of the way culture treats us, right? Culture ends up treating us this, but then the textbook comes out and says otherwise. So now we've got map projections. A map is a flat representation of Earth's curved surface. However, transferring a curved surface to a flat map results in a distorted image of the curved surface. An area shown on a map may be distorted in size, shape, distance, or direction. The larger the area being shown is, the greater the distortion tends to be. A map of the entire Earth would show the greatest distortion. A map of a small area, such as a city, would show only slight distortion. Okay, so they're kind of I think here they're talking about a lot of different maps, but it's interesting because let's remember that. Okay, they're talking about big maps show a lot of distortion, and then small
That's
maps
what we were
show
just
little
talking
maps.
about.
Yeah.
That's what we were just talking about, with the globe being a generalization, and then the more you zoom in, the more detailed your map is going to get.
So,
that's just,
when and where do they calculate for distortion on a map is my question.
Say that again?
When and where do you ever calculate for distortion on a map? So I think about if I were to have a piece of paper and I crumple it all up, and because that's what you do is you take a globe and then you wrap a paper around it, and that paper is going to tear as it tries to expand to a globe. But at the same time, that's not what the globalists claim. They claim that you're taking a globe and then you're trying to flatten it out on a piece of paper, which is going to cause a lot of stretches, right? And so where do you see them making all these claims to, okay, we've got to adjust for the distortion of the map now. This area is going to be a little bit more stretched. You don't really see that on road maps. They say it.
No, because you wouldn't. That's because it's like it says, it's almost unnoticeable when you get to the smaller local maps. So you don't even notice it. You're just looking at where you are locally as a human on this, in your little tiny, spot that you're navigating on this huge Earth. It's like the scale difference is so huge that when you're just navigating around where you're going, like there's no way that relates to the whole entire Earth at the same time. Like, it's two completely different things.
Yeah. They're saying that there's slight distortion, okay, on city maps. So
yeah, but probably not so much if it's just a city. They'll say slight, but
it's
you're not
so
gonna notice
slight
it.
that you don't take it into account whatsoever is kind of the big deal. They're acknowledging that there's distortion, but then you just treat it as if there is no distortion. It's the whole thing. And so when it comes to, I'm thinking about magnetic declination, about how you have to constantly kind of adjust your compass with the true north versus magnetic north, right? And so that right there is an obvious place where you have to make adjustments and correct for distortion. You know what I mean? But when it comes to,
is that really distortion, or is that this is the direction that you're traveling in?
You're right. So it's I'm sorry, I didn't mean to call magnetic declination distortion. I'm just saying,
but I can see how you think it would be, though.
Yeah.
Related. And it
I understand
probably somewhere in between lies where that confusion happens.
Yeah. I understand there are flat earthers out there who say that magnetic declination is a myth and it's a hoax. It's all about just correcting for this distortion, right? But that's
Yeah,
not true.
that would be
like we've
incorrect.
discussed that in the past. Yeah, we've
Yeah.
discussed that in the past and said magnetic declination is very much a thing.
It is very
Yeah.
much real because you can measure it yourself. If you spend one sunny day, measuring sun shadows, you'll see that the point that the sun rotates around and the point to where your compass allegedly points to, it's not really pointing to the pole, it's following a magnetic flux line, but doesn't matter because either way it's not the same spot. But if you take the time to measure the shadows, you can see for yourself that the point that the sun rotates around and the point where your compass points to are two different places.
Yeah.
And the difference is your magnetic declination.
Yeah.
And if you don't want to do it during the day, you can wait for the full moon, and on the full moon at midnight, it will be exactly. You can line it up again on your axis,
And you can use Polaris
use Polaris, and exactly knock it up just
instead of
like
the
that.
sun. Just use Polaris. Yeah, exactly.
Mm-hmm.
Yeah. Polaris has been traditionally the thing that we always use for pointing to north, right?
Yes. Even when you're using like an equatorial melt where you want to track the sun or the moon or anything in the sky, you align it to Polaris.
Mm-hmm. Yeah. That's a really big thing that stands out to me when it comes to latitude and longitude that I didn't quite get into last time, and that is concerning Polaris. So,
Mhm.
yeah, on a straight line flat model, pretending there is no refraction, the farther you get from Polaris, the slower the angles change.
Yeah.
Okay. This means on a straight line flat model, pretending there is no refraction, the lines of latitude would have to be unequally distanced. Okay. Unequally distanced. And so on the globe, are you still there? I was hearing a bunch of static.
Yeah.
Okay. So on the globe, each of the lines of latitude are equally distanced. I'm hearing static again. Wondering where it's coming from. Is that?
I don't know.
Why am I hearing that? Is anyone else hearing the static?
I think that
Okay, static's gone.
Cammy. Oh, now she's putting. Okay, there's something going on with Cammy's sound. Okay.
Okay. Don't want to lose you, Cammy.
Okay, go ahead.
Okay. So this is where I kept all of the lines of latitude equally distanced, and you're trying to look at the angle at which you see Polaris, and all of a sudden you got weird refraction that would have to take place in order for this equal distance to be when it comes to lines of latitude. And then over here, I have the refracted flat model with unequally distanced lines of latitude. And so here I've got, it's smaller when you're closer to Polaris, and then as you get farther and farther away, your lines of latitude get wider and wider. So if someone wanted to really put their world to the test, what they could do is go out and try to like physically measure the lines of latitude, trying to go in a straight line. Okay. Each line of latitude is not evenly spaced because downward refraction limits our range of view over distance. Okay. This is our refraction that's getting sent downward, and that's
where is the data coming from that you're putting that's I don't get it.
Okay, so what I did was I kind of created my own model here where I did each one is 10 degrees apart. Okay.
Mhm.
And so at 0 degrees of latitude, you're supposed to see Polaris at like right on the horizon line. You're not supposed to see this would be at the equator. You're not supposed to see Polaris at all. Okay. And then you go up 10 degrees of latitude, and that's where you're supposed to see Polaris. Is
Okay.
you're supposed to see at 10 degrees in the sky. Okay. And then it kind of goes on. And so I'm trying to use this protractor to measure out the different degrees based on where I'm at. Does that make sense?
Okay, but I don't understand why the yellow lines are bent.
Uh,
What does that
the,
mean?
the yellow lines are bent. It's just kind of an expression of downward refraction. Okay.
So there's more refraction
I can't make
the
this.
closer you get to Polaris.
There's okay. In order to do this, okay, I couldn't put this star super, super high up in the sky. Does that help a little bit?
Okay, well that makes more sense. Yes. Okay.
Yeah. And so I only did that just for the sake of expression.
Okay. Okay, I get you. But when you're showing it, like if for me, because I like know how refraction works, I'm thinking there's this line, and then there's like more refraction the closer you are to underneath the star, then the further you are away, which is like the
Yeah.
opposite of actually how it should be.
Yeah. I'm not trying to say that there's more refraction. Sorry, it's a little off-putting with that. Yeah. It changes as you put this higher. Does that help it at
Yes,
all?
there you go. Leave it
Yeah.
like that, and then move your
Okay.
thank you.
Okay. It's still a little weird right here, but yeah. Uh,
But
it's
it's better.
hard to it's hard to do this over distance because it's not to scale. Not to scale.
Okay.
It's just kind of there to convey a point. So hopefully the point is made. I also think about how even with I've been thinking about this example of looking down into a pond and seeing a fish in the water, and how even if you're pretty close to being up above it, you're still seeing refraction to a significant degree. And so even though this laser is not like super down low next to the surface of the water, it's still getting a significant amount of refraction there.
Right.
Yeah. And so that same concept is going to apply to uh, starlight and the sunlight as it comes down into the atmosphere. People just say, oh, well, it's straight up above us and it's not going to have any refraction, but just a little bit off and it's going to start having more and more refractive effects.
Yeah.
And that's all going to have an effect on map making if we're going to try to do accurate depictions. And so this is where
Well, that's correct, because whenever they're making a map, they're basing it off the 90-degree position from that point of land to the star, right? So, yeah.
Yeah. So when it comes to earth science, so much of it, and it's a real shame that it gets so departmentalized in college, when in high school it's all kind of treated in one category. You study it all together at once. But in college, it gets very departmentalized. You only study astronomy, you only study geology, and you don't really see the overlap. When this is a really great example of how our understanding of astronomy can affect our views of cartography, right? When we understand meteorology, the way the atmosphere ends up getting factored into our views of astronomy. And yeah, all these things kind of end up coming together. And that is going to help us to make better maps, hopefully. You follow?
Yeah.
So it's all
But
about kind of, go
it's
ahead.
really hard to make a map, though, especially
Yes,
of the
it is.
entire world.
Yeah,
It's
especially
like
because
extremely hard.
yeah, you start climbing mountains and going through trees, trying to do a map when you're constantly doing switchbacks up and down a mountain and through a forest, and you can't even see the stars. Yeah, it's going to get really hard really fast. So there's a lot of room for margins of error here.
Oh, yes.
Okay, I'll go ahead and read this one right here. Over the years, cartographers have developed several ways to transfer the curved surface of Earth onto flat maps. A flat map that represents the three-dimensional curved surface of a globe is called a map projection, which is interesting because if we're calling if we're just making a flat map and it's not representing a globe, then can we really call it a map projection?
But see, what's funny is that line you just read is actually the opposite.
Yeah, because
They're transferring the flat surface of Earth to the perceived curve of the sky, the
Yeah.
sky dome, right?
So you
Like
got,
that's how
Mhm.
we navigate is by the sky.
And so this is kind of going right back to what we're talking about when it comes about art, and you've got your person that you're painting over there, and then you have your drawing, and so many people are saying, oh well, I'm drawing a globe because that's what they look like, but that there's so many preconceived notions that go into that. So they're showing a globe, but we're over there saying, no, that's not a globe, that's a flat earth. And so our picture looks completely different. And so that's where it really comes down to, what are we drawing actually? And so our big claim is the exact opposite of what the book is saying here. The book is saying that the earth is a globe, and so we're trying to depict a globe, and we're saying no, the earth is flat, and so we're trying to depict a flat, and each person is pointing a finger at the other saying you're wrong.
Pretty much.
So, no projection is an entirely accurate representation of Earth's surface. However, each kind of projection has certain advantages and disadvantages that must be considered when choosing a map.
So Kyle, what I have up in my clip, by the way, is a backwards. This is how they plot the sky, and then how they flip it to a globe.
For a second.
Yeah. So I think that's fun because because we see the sky is flat. So this is how we plot the sky, and then they're telling you that this is how we take the way we see the sky, and this is how we spin it on the globe. So I think it's fun because they are showing you just the backwards of it. And again, because we see the sky flat and they have to plot it flat. So I thought that would be fun to put out. It's kind of goes with what you're doing, but backwards a little bit.
Yeah. One of the things that stood out to me about this paragraph is how they're not throwing out any projections, right? They're saying that there's something valuable with each of these, even as wonky as they can be sometimes. I'm kind of looking over at some of the, like these maps over here in the college textbook, right? And so they're showing all of these things, and they're kind of presenting value in each map. And so many of the globalists out there, they just thrash the Gleason's map. How many of you guys have ever like heard anyone say that the Gleason's map is useless? You can't navigate on the Gleason's map. I've heard so many trolls say that, right? But here they're not throwing out any kind of projection whatsoever. They're saying that there's use for all of these different kinds of projections out there, all these different forms of maps, even if you kind of stretch it in weird ways.
Well, they all use the same Cartesian coordinate system,
Mm-hmm.
and they just map it across different surfaces. So you can't say that the Gleason's map is garbage and then say that the globe is right, because it's the same Cartesian coordinate system placed on different surfaces.
Yeah, absolutely. Although it's weird calling it, because we like to look at it. That's exactly what they're talking about right here, is these different squares that are similar in size, and they're trying to make it more Cartesian-like compared to this pointed thing where all of the kind of comes
map.
together. This is much less Cartesian-like. Okay. Imagine Earth as a transparent sphere that has a light inside. If you wrapped a cylinder of paper around this lighted globe and traced the outlines of continents, oceans, parallels, and meridians, a cylindrical projection shown in figure 2 would result. Man, I really don't like the way that's worded.
Nope,
Meridian. Go ahead.
if you did that, this is what would result. You'd have this.
Yeah. Mm-hmm. So
Mhm.
I feel like the writer just could have said that.
Well, it's a typical Mercator projection, or it's like what was in most classrooms when we were growing up, where the poles are stretched out to infinity. And it makes Greenland look giant and Canada look giant.
Yeah.
I thought it was cute because on one of the shows I'm watching, which is like Emily D. Baker, but she has a new logo, which is this spinning globe, a pink spinning globe. But what catches your eye about it is it's the pink spinning globe, and yet Greenland is still huge. Doing on the top portion, it's like it's giant, sitting up there about as big as North America. So even on this, it's like, oh, come on, you guys, if you're going to do that, at least you have the angle, do the proportions. But they did the spinning globe with the Mercator size and things on it, so it was whack.
Yeah. Oftentimes, stuff like this we've talked about in the past, how they use them for political reasons to try to make Russia look bigger, and so they really emphasize that. And so a lot of things
they can make
work for
America
different
look
reasons.
bigger and Africa look smaller.
Yeah.
Yeah.
Mm-hmm.
Some of them, like, I mean, having played with maps over the years, in Photoshop and stuff, it's like they all stretch out the North Pole more than the South Pole. So they'll make Antarctica look small, and then the North Pole is huge. And then, and then the equator will be like not in the center of the map. It'll be like closer to the bottom because the top is bigger. It's just weird, the stuff they do with maps.
Yeah.
But the other weird thing is like it doesn't really matter. All the land masses are still recognizable. It's just weird.
You can still navigate using this, even though
well, nobody navigates using an entire world map. Everybody's whenever you're navigating locally, because you don't care about the other side or 1,000 miles away when you're a little person in a forest. It's inconsequential.
They might put those maps in the planes, right? But that doesn't mean the pilot is using that map.
Even in a plane, you don't need a world map, know?
In a plane, they keep you on very, very tight little routes. I mean, they do the little routes that go over the channels, they say with the jet streams and that, but they keep you on your little channel and you don't go outside of it.
Yeah. I've heard about that. And when it comes to planes, they follow the same flight paths, and they'll kind of follow the person right in front of them, like all the way there. And that was
and there's ETOPS. There's something called ETOPS where it's like emergency land, whatever. Anyway, any commercial flight is not allowed to fly outside of a certain distance of any airport at any given time. So like there's a max distance that the flight can be from an airport. Like if they have a diversion or an emergency, they have to fly within limits of these airports that can serve them if they have an emergency. So a lot of times these flight routes and stuff, it's got nothing to do with the shortest flight or, whatever, or, it has to do with where the airports are and what the flight route is. And is there an emergency landing within a certain amount of hours based on the jet and how many engines it has and how much fuel it can carry. So that will also alter the flight path, the type of aircraft you're flying on. So it's like a lot of these flight paths and things that people try to use as proof don't really prove anything, because they have to follow these stringent guidelines because they're commercial and they're carrying
very
people
departmentalized
and stuff like that. Exactly.
Yeah.
So
it's interesting how much credit people give to pilots acting as if they were open world explorers, but
they're acting like they can just fly wherever they want to go. And why don't they just go this way? And why don't they just go that way? Well, because there's a whole
with
bunch
their blinders
of things.
on.
Yeah, there's a whole bunch of things in place. Like when you're talking about like transporting people, like human lives and stuff, and you where it could cost you lots of money, things change drastically. You can't just do
Yeah.
whatever you want.
Yeah. They've got tunnel vision. Tunnel
Mhm.
vision. You can only see those this much, and so yeah, there's reasons for it. Not all uh, it's not all conspiracy. A lot of it makes sense, but I can't say that there is no conspiracy in it whatsoever.
Well, there's just not a lot of conspiracy when it comes to like commercial jets and stuff, because
Oh yeah,
there's safety regulations and blah 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 blah. It's
yeah,
just,
we're not getting into like jet fuel hoax and stuff like that. Don't worry. Not saying I believe in that. So
well, because they do use fuel.
yeah, they do.
I mean, if you go and watch anything online about jet, jet tragedies, any sort of crash or anything, first thing air traffic control will ask of the pilot is how much fuel and how many souls on board.
Mhm.
So
I think I heard somewhere that they dump their fuel before doing any kind of emergency landing, just
sometimes,
so it doesn't blow up.
yeah. Well, okay, I
Right.
actually experienced that because when I was flying back from Balaton, we left from London and the plane took off in London and we circled around the airport for an hour and a half. And then they were like, "We're going back to London. We're having a problem." But I
Wow.
mean, this plane took off loaded with fuel to go all the way to New York.
Uh-huh.
And they literally flew around for like an hour. They just flew
Oh
around
my
and then they
goodness.
landed. It was kind of wild.
It kind of goes to show that they go over prepared. I was listening to uh PhD Tony the other day. I had a big debate with PhD Tony, and he was going
I
on
do
about
remember, I don't
they have
remember
to
a
have
whole
the
lot about
exact
the
amount of fuel.
conversation, but when all of this people were doing the jet fuel hoax, because we lived right by Denver International Airport, Bob found somebody that was a friend of somebody else that what he did was he fueled jets. That's what he did day in, day out, and was out on the tarmac fueling jets. And I know they talked at length on it. And Bob was also, again, a pilot, not a commercial pilot, but a little fun pilot, a little
Mhm.
recreational pilot. And that, so he's very
They
familiar
have a
with
little bit
planes
more
and that.
freedom.
hmm So I know on the things that he was not a believer that they flew without fuel because it didn't work. In other words, it didn't pass the little reality test as far as actually doing a little bit of research going further on it.
Mhm.
Did he think they could on some of the flights hide it with efficient engines? In a way, yes or no, because they were really marketing the high efficiency engines. It's not really a big secret with the vortexes and that they tried to make them gas efficient. So but you're right, they asked souls and weight, and that's what I was gonna say too, is usually I don't know if they dump it as much as like what Karen says, they burn the fuel, they just go
They'll
for a
just
while.
dump it. That's what I'm saying. Like this flight I was on, they flew around and dumped fuel, and then they flew back to the airport, and then they put us all up in a hotel for the night. And I had to stay an extra day there before I came home, but that's what happened.
Yeah, and yet globalists will point to flight times and like they prove everything when they do crap like that,
Yeah,
you know?
it really doesn't prove a whole lot either way. There might be some specific flights that may bring up questions about certain things, but for the most part, I mean, the lack of flights that go from like the southern end of one continent over Antarctica to another, like a flight that would go very simply over over the pole, like from South America to Africa or whatever, like they do in the north, because there are flights that kind of, you know, go by the North Pole. They kind of skim it, and it just isn't the same in the
Mhm.
south. So there's things like that
Yeah.
that bring up questions. Anyway, I digress. We're getting off topic of
Oh,
your.
you're fine. You're fine. So this paragraph just goes on and talks about this and how it's not throwing it out the window because of the distortions in it, but it's acknowledging that it is distorted, but people still use it. They still use it for different purposes, right? I'll go ahead and skip over that and get on to the meat and potatoes here. Okay, with azimuthal, or sorry, there's a way to pronounce it. Okay, that sounds funny.
Azimuthal.
Azimuthal. Yeah, I don't know anyone who actually calls it that. Not very many. Azimuthal, but
I
it's
say
got a Y in there.
azimuthal.
Azimuthal. Right? Maybe I need to say
Azimuthal.
that more often to sound better. Why are they adding a Y? Myuthal. Okay, so azimuthal projections. A projection made by placing a sheet of paper against a transparent lighted globe, such as the paper touches the globe at only one point, is called an azimuthal projection. I don't get what they're doing with this whole paper, like the, the writing thing, but yeah, we get what they're talking about. Okay. Azimuthal projection, as shown here in figure 3. On an azimuthal projection, little distortion occurs at the point of contact, which is commonly one of the poles. However, an azimuthal projection shows unequal spacing between parallels that causes distortion in both direction and distance. This distortion increases as distance from the point of contact increases. So they're calling this distorted compared to their globe. And again, we're pointing at them and saying this is more right than the globe is. Okay. Despite distortion, this is the paragraph that you really want to pay attention to. Okay. Despite distortion, an azimuthal projection is a great help to navigators in plotting routes used in air travel. As you know, a great circle is the shortest distance between any 2 points on the globe. When projected onto an azimuthal projection, a great circle appears as a straight line. Therefore, by drawing a straight line between any 2 points on an azimuthal projection, navigators can readily find a great circle route. Okay, so right here, they're really playing up the advantage of this projection, okay, which we can look at as the flat Earth map. That's the whole concept. You got north in the center, and then it gets wider as it gets farther away. And here they're talking this up as kind of the best projection out there, as far as I can tell here, right? And they're talking about with air travel, and this kind of brings up the Hammond's air travel map. Okay, and this is Hammond's air age map of the world, and this one's totally claiming it's a globe, but you can see that this is the flat Earth map here entirely. Important to note that this one was made in 1948, and the Gleason's map was made in 1892. And one clearly looks like it's just modeled after the other. And one thing that really stands out to me is right here, we're noticing a scale. And so on this whole air map of the world, you're seeing really tight scale around the North Pole. And then as you go farther and farther south, the scale changes. And that much has stood out really strongly to me. And a lot of people will point fingers at the Gleason map and say, oh, well, this is actually a globe because it says projection. Okay, projection is what they'll continually call it. Okay, on the projection of modern college. Okay, and so people will criticize that for that. But I want you to pay attention to the scale on this. A lot of people ignore the scale on the Gleason map. And this Gleason map scale is constant. There is no changing miles as you go farther south. And so that's a big way this Gleason map is different from this air map. I think that kind of goes a lot because a lot of people are wondering about if Gleason really was a flat earther. I'm like, if you really doubt whether or not Gleason was a flat earther, you gotta read his book. He wrote this great big book.
Well, there's a whole book. It's called "Is the Earth a
Yes,
Globe?"
that's
You
the one I'm
know.
talking about.
Yeah.
Yeah.
I
Is the
wonder if
Bible
that
from
air
heaven? Is
map
the earth a
isn't
globe?
more accurate. Isn't just a little bit more accurate than the traditional Gleasons.
Yeah,
It's
it's a
not
little.
quite as
It's
condensed at
got
the
some
top.
slight changes.
It's not quite as condensed at the top, and Africa is wider at the bottom.
Right.
Uh-huh.
It's very important, actually. It does have.
It's got some slight differences that I'm noticing just because I've looked at the Gleason so much, and I look at the
Uh-huh.
air map, and
Mhm.
I'm like, that might be more accurate actually than a
That wouldn't
traditional
surprise me.
Gleasons.
This is something that we were talking about before this show, Kyla and I, just as they pop up and looking at the trade maps. It's a really good one to look at. If you
Yeah,
go big on the back of the
exactly.
trade map,
Follow
when
the
looking,
money,
follow the
commerce.
money, commerce, and this. These are trade routes, and these are areas where they can't lie to you quite as well because there's a lot of trade going on. So if you look between South Africa, go back, Kyle, between South Africa and
On
or
the
not
other
South,
map or this
no,
one?
yeah, that one, Africa
Okay.
and South America. So bring the two continents up
Uh-huh.
and see how, like, again, do you see the little pedal there? And they have that little jump over, that little red line jumping over,
Uh-huh.
Right
and
from
different
the
things
western
there.
tip of Africa to the eastern side of South America.
Oh yeah.
You have a
Mhm.
lot of flights and everything. In fact, all of the flights that go to Africa jump up there to jump over. They don't notice how all these flights like pop down and go down there. So
Mhm.
they also lay cables there. There's a whole bunch going on there. So one of the first things I always look at when looking at all kinds of maps is, do they have that area like completely across each other on the map? And is the distance between it like equivalent to 4 or 5 North Americas? Because you see that a lot. You see it on a lot of the maps. Like when you guys talk about that Japanese map with all the extra continents going around,
Uh-huh.
or
Mhm.
It's Japanese. Huh.
and, I know it was like Antonio's the map of the sun and the different ones. And this is like some of the keynotes that in reality, you know that this can't be an area. There are areas, you'll notice in the Southern Atlantic, which we call the South Atlantic anomaly. Nothing goes down there. See how there are no lines, and down here how they have it split. That again, nothing goes down there. Also in the South Pacific, you'll see different areas. So you have all these areas where you don't have anything going.
Mhm.
That's where your lives are going to be. So
Mhm.
remember when I made that turtle map and it's like I couldn't cut through things. It's like no, you can't cut through the main trade lines because there's too much going on through there. So when we
Mhm.
were doing that, it's something to look at when looking at the maps, like how real could they be?
Yeah. So when it comes to this is a really big deal because how many times have you heard trolls say you can't use a Gleason map for navigation? You can't use it for navigational purposes. It's useless. I don't know. That's just kind of the troll crap they throw. But this is, yeah, very something that people use this kind of stuff for navigation
It's showing a route, but ultimately nobody's using the whole world map for
Yeah.
navigation locally. They just aren't.
locally.
It's
Yeah.
impractical and it doesn't work.
hmm Wait, so the whole map, like I'm not aware of. I don't really know enough pilots to really speak on their behalf, but I'm not aware of any pilots who actually
They're not
pull out a map and
looking
follow
like
this
a
along
pilot
either.
flying from New York to LA is not going to care about what's going on between India and the Philippines and Australia or Africa and South America. You know what I'm saying?
Yeah.
Like they're looking locally at where they're at. They're paying attention to where they are locally, and that's where the magnetic
The
declination
blinders
comes
on.
into play.
Yeah.
Because they have to be at a certain pointing a certain degree in a certain direction to land on. They have to bring the plane in to land in at these airports in a certain direction.
Yeah.
So they're not worried about the other side. They're looking locally at where they are, just like everybody else. It may be a little bit bigger of an area because they're on a plane and they're flying so fast. But ultimately, it's there. Nobody is using the entire world map to navigate locally.
Yeah, because that's
Nobody.
the opposite of what local means, right?
Exactly.
Yeah. Yeah. So, despite distortion, wait, did I already read that one? Yeah. Despite distortion, an azimuthal projection is a great help to navigators in plotting routes used in air travel. As you know, a great circle is the shortest distance between any 2 points on the globe. When projected onto an azimuthal projection, a great circle appears as a straight line. Therefore, by drawing a straight line between any 2 points on an azimuthal projection, navigators can readily find a great circle route. And so when they're talking about great circle routes, if you try to draw a line on a globe, it's going to go swampy. But
That's not even how an azimuthal projection map is used, though.
mhm.
If you look at the AE map, it says longitude and time calculator. And if you can't measure a distance, like you can't measure from Russia and then measure to like Rio de Janeiro and be like, it's X amount of miles, because it doesn't work like that. You measure
Yeah.
from the center pole to Russia, and then the center pole to Moscow, say, and then the center pole to Rio de Janeiro, and then you go around that, which makes the great circle, which tells you in time how many hours away sun time it is, right?
Yeah.
So it's like you
I'm glad that
don't
you're
measure straight
mentioning
lines
sometime.
like arbitrarily from city to city across the Gleasons, because that's not how you use the map to measure distances. It says
Yeah.
right there, longitude and time calculator.
Yeah.
So their description of how to use the map is incorrect.
Whose description?
The thing you just
books.
read from the book,
text.
where it's
Okay,
like
the
if you
textbook.
measure a straight line from such and such place to this place, no, you have to measure it from the pole to the city and then from the pole to the other city, and then you measure it through time. Anyway,
Yeah.
sorry.
That part kind of caught me as I was noticing over here. You've got time zones right here going
Yeah,
all the way
because it's a
around.
time
Yeah,
calculator.
and so it's the exact same thing as what we're seeing over here. You can see the influence of how this has influenced this,
Mm-hmm.
with the times going all the way around, and it's used the exact same way. And so the time calculator, for those in the audience who don't know what that means, is it's used for calculating time zones. And so if you're right here, you're in one time zone, but if you're over here, now you're like 2 hours ahead, right? So you got 1 hour here, 2 hour, 3 hour, and so that's like a 3 hour time zone. Okay, going all the way around.
Mm-hmm. Yeah, each one of those little pieces of pie is an hour
Yeah. And
of
so
time.
this whole thing is not made to be confusing. It's made to be as simple as possible. It's advertised as being simple enough that a child could understand. And when you start to like have some people will put hands on this like a clock, and people get all confused when they think about analog clocks and like, okay, you're making it too complicated. But it really is just that this is one time zone, and if you're over here, okay, you got 1 hour, 2 hour, 3 hour, and that's
Mm-hmm.
how many things it is. But yeah,
if you
time
put
zones.
if you put a little sun on the hour hand, that
Mhm.
works.
Yeah.
And just align it to your time zone.
Hmm. And so it kind of does that, though we understand time zones are very political. And so
Yeah, but if you
yeah,
ignore the political part and just go by where the sun
yeah,
is at noon, it
yeah,
works as a clock.
yeah.
Longitude and
The
time
way that's the way
calculator.
it's designed. Yeah.
Exactly.
Okay, so we're almost done here. A projection is made by placing a paper cone over a lighted globe so that the axis of the cone aligns with the axis of the globe is known as a conic projection. Okay, another mouthful. The cone touches the globe along one parallel of latitude. As shown in figure 4, areas near the parallel where the cone and globe are in contact are distorted the least. Okay. Exactly how this cone is different than this one, I'm kind of a little bit lost on that one. So that's a little weird because these seem to be very similar to me, but maybe it's just kind of stretching it out a little bit more.
Well, it just depends on how sharp they want to make the cone. See, a lot of this is subjective. It's kind of
Okay.
I guess it's like the halfway between point, but between like the sky objects and the Earth right there. It's almost
Yeah.
like an orthographic projection of the North Pole,
Mhm.
kinda, sorta.
Yeah. But I think that's kind of the main thing. The last little bit here, I really wanted to put the emphasis over here on how the Gleason map is useful and how the textbook acknowledges that, which is a really big deal. The rest of this stuff is some pretty basic stuff when it comes to map reading and stuff like that. But I did have a video or two I'd like to share about interesting plane flights, if that's all right. And then I think we're going to call it good. Window. So this is, okay, emergency plane landings. Can you hear that? Is it quiet? Because sometimes we have that issue. I'm trying to avoid that.
It is quiet, but I'm not complaining.
Okay.
Is there subtitles, maybe?
Yeah, there's subtitles. Hopefully that worked.
So it's an emergency landing, right?
Yeah, he's talking about an emergency landing. It was a flight from Taiwan to Los Angeles, and so on a flat map, we've got a straight line from Taiwan, and they're having an emergency landing right here in Alaska. And so,
Mhm.
looking at the globe, it didn't make sense, but looking on this flat Earth map, it makes perfect sense.
Mhm.
Okay, so that was really interesting. A lot of when it comes to plane flights, a lot of people like to think about a different one, which would be between Santiago, Chile, and uh, Australia. And this was really interesting to me. That just I thought was well worth sharing.
By the way, was you're looking at this, that map that you have up there would be one of
Uh-huh.
those that I would call
This
a
one?
terrible map. Yeah, if you
Yes.
look at it.
Yes. I
Yeah.
was
So
thinking
see
the
that
same thing because look how far apart South America and Africa are. In
Yeah.
reality, they are not that far apart.
it's
You're
not
right.
going to take you as much
You're
to
right.
pop across as it will to pop across the country here. So again, little things like that. When you start looking at that, you'll start looking maps a little bit differently. That does not work in reality.
Yeah. So one thing that so despite the map, okay, what I want to share with you is what they found, their explanation on that. But yeah, great observations when it comes to that whole gap between South America and Africa. That's a great observation.
Now, I don't know if anybody else is hearing it. 'Cause I don't
I
hear a
can't hear
thing,
it.
but that's
Oh,
been
I
a
wonder
lot with
if I can
the
fix
stuff
that.
I'm listening to.
Yeah, I
Even you
can't
talking
hear
right
it.
now, Kyle, I don't hear
Oh
you.
dear, having a hard time hearing that. I wonder if
I
there's
don't
a
know
way
why
to.
you don't hear him talking. That's weird.
And just there it popped in with you talking, Karen, and then when she popped in, I could hear him a little bit in the background. It's crazy. It's wacky. I haven't ever had this problem. It's a new
Why
problem.
don't do you want to try leaving and coming back to the StreamYard? Probably should
I
have
can,
done that a
except
long
for
time
I
ago.
think I think we're just finishing up.
Okay. Yeah, this is really just it. But okay. Where'd it go?
I still don't really hear it.
So he's talking about Mick West and about how Mick West is saying the planes fly way down here and come all the way over here. And because of this weird plane flight that he's claiming to, he's saying that Mick West is disproving the flat Earth by this weird plane flight. Yeah, this famous one from Australia to South America.
Uh-huh.
Okay. And what he's going to point out here is interesting. Where'd it go? Here's something that they won't tell you.
Tracking the flight from Sydney to Santiago, Chile, and it's picked up by the Australian ATC radar. Okay, this is the Australian Arctic radar system that tracks the flights across the Pacific. Australian ATC radar is controlled by these guys. Who's these guys? NASA. Yeah, the same guys that brought us the fake moon landings and the fake going to Mars and the fake ISS space station.
Okay, so that's really it. So I just wanted to point out that these long distance flights are controlled by NASA. I'm like, what? They're not going into space or anything like that. They're doing this whole thing, and that is raised a lot of suspicion for me. Why does NASA have to have their fingers in the pie?
Is there any other flights controlled by NASA, or just the ones that get close to Antarctica?
It's these weird flights that the
or
globalists
just the
are pointing
far
to.
south, the southern flights.
Most of the dream flights, the really, really, really long distance flights we were looking into, and especially the ones that, again, you don't look through the windows and they're all entirely, like, again, they put a scene on it where you're looking at supposedly through the cameras on the other side, and that you're not looking through the windows. Those all go through Doha. We were looking into that a long time ago. But they all seem to go through one airport, which is U.S. So we got, again, a lot of interest there. But yeah, it seemed like we went on that bandwagon years and years ago, and there was something there to it. There was a lot there. You can really go down that rabbit hole, and they maybe change things out. But all the long flights were all going through again that one airport. So we thought that was really fascinating.
Yeah, that was the main thing I wanted to share with you. It's just the weirdness of NASA being involved in long distance plane flights and how they're controlling all that. And so it's like, why would they need to do that? It's not even US territory, right? Australia, South America, what does the US have to do with any of that? But NASA over there has to be in control of that for some reason. Yeah. So anything else you guys have to share?
I think we have a new promo for Esoterica that's gotten a little bit longer since the last show, and we're going to keep on growing it every show.
Okay. I still have the last one. If you have the new one to share with me, if you could just drop that in the chat, I can grab it, and then I can share that one instead, if you'd rather.
I'll give you the new one. I'll put it here in chat.
Esoterica World. Which chat are you putting this one in?
Well, here in the private chat.
Okay.
In StreamYard. Or if you want me to play it, I can try to play it. Okay. Whatever you want to do.
I think I got it. I just hope that the audio works.
Share with
Oh.
sound. Are you sharing with sound? Does it give you that option?
Okay, I'm going to try to share it here. I thought it was sharing with sound. I don't know if anyone just didn't hear it at all or if it was just quiet.
I've not been hearing sound on your videos, so I
Oh,
don't know.
okay. Share screen. Okay, it says share tab audio. Okay, that should work.
Mm-hmm.
Solve the mystery. Esoterica, Music and Art Festival. Decode the mysteries of the occult. October 17th, 18th and 19th, 2025. Happening in Spartanburg, South Carolina at the music camp. Fire. Water. Air. Earth. Ether.
Featuring Austin Whitsitt of Whitsitt Gets It. Live music by Chief Crow. Mario Garza of Symbolic Studies. Artist Watson Atkinson. Live music by Alex Lowry and Christopher Crum of Don't Follow Crum. Plus more to be announced.
Decode the mysteries of the occult. Gain wisdom, shed fear. Esoterica. Go to esoterica.world for tickets and for more information.
Okay. Thank you all for watching, everyone. It's been a pleasure having you. Do you have any closing statements you'd like to share with us, Cami?
Everybody have a great week, and we will see you on Sunday.
Okay. See you
Yes,
Sunday.
thanks for being here. Have a great evening, everyone. Evening.
Okay. Peace.